Friends, you already know that memory forms an essential component of any microprocessor-based system. In the very first lesson, you have seen the basic idea about memory. In this lesson, we will try to consolidate those basic ideas and will discuss some of the finer aspects of memory and the design issues. Here we will discuss memory organization, working principle, and various functional classification of memory. Memories are used for storing information in binary. Conceptually, a memory chip is an array of registers, each register storing one memory word. The width of each register is the number of bits per word. We should make a distinction of system word and memory word. System word will vary from computer to computer, ranging typically from 4 bits to 64 bits. System word may be equal to or integer multiple of memory word. From the system point of view, memory is organized as W into B, where W stands for number of registers or locations contained in that memory block, and B represents width of each register in bits. Common values for the number of words per chip are 1K, 2K, 4K, 8K, and so on. You have noticed they are all powers of 2. And common values of the word sizes are 1, 4, and 8. Now you must know what is addressing. The address of a memory is used to distinguish from one location with the other location uniquely. This is just as you have seen in the case of a pigeonhole in a post office. Numbering of registers or memory location starts from 0 and continues as high as needed. So with n-bit address, the contents of any of the 2 to the power n memory locations can be accessed randomly without the need to sequentially traverse the preceding locations to get to the specified location. For this reason, this type of memory is called random access memory, abbreviated as RAM. You already know there are 2 types of RAM: read-write memory RWM and read-only memory ROM. However, commonly the abbreviation RAM are used for read-write types of random access memory. RAM may be classified as static RAM and dynamic RAM. Static RAM is a read-write memory in which data are stored in flip-flop storage elements. The general model of a static RAM consists of n-bit address bus to select any of the 2 to the power n locations, m-bit bidirectional data bus, read-write bar input signal, that is, a high for read and a low for write operation, and a chip select CS bar input. If the chip select is activated, a particular chip out of many will be selected. On the other hand, when the chip select line is not activated, data lines of the chip are put into a high impedance state and the chip is deactivated. In contrast, a dynamic RAM is a read-write memory in which data are stored as electric charge on capacitors, which require periodic refreshing to retain data bits. Each bit cells must be refreshed approximately at an interval of 2 milliseconds. A dynamic RAM has n-bit address lines, separate m-bit data in DIN lines, and m-bit data out DOUT lines. It has control input lines which are row address select RAS bar lines, column address select CAS bar lines, and read-write bar line. To reduce the number of pins, the address RAS bar and CAS bar lines are used to address 2 to the power 2n locations. Commercially available dynamic RAM memory chips are usually single-bit registers. The row and column organization ensures simultaneous refreshing of all cells within one interval. A comparison of dynamic RAM versus static RAM will show a distinct advantage of dynamic RAM over the static RAM. Dynamic RAMs are more compact than static RAM. The cost per bit of dynamic RAM is substantially less than that of static RAM. Power consumption is also significantly less than the static RAM. Dynamic RAM is slower in operation. It requires an additional refresh circuit. Let us now discuss about the read-only memory ROM. Various variants of ROM are available. The contents of ROM are mask programmed by the manufacturer. The contents cannot be altered afterwards. In programmable read-only memory, abbreviated as PROM, the contents are programmed by the user only once, just similar to photographic plate or film. Erasable and programmable ROM, abbreviated as EEPROM, where contents can be erased by ultraviolet light through a quartz window. And the contents are programmable more than once by a device known as PROM programmer. The contents of electrically erasable ROM, abbreviated as EEROM, can be erased by the application of electrical pulses. This is also known as electrically alterable ROM, abbreviated as EAROM. Here, contents may be erased electrically and programmed in circuit. In most cases, single memory chip may not provide the sufficient storage space. So, in those cases, we require to cascade the memory chips to provide the required storage block. Now let us see how memory word size can be extended. Suppose we need to realize a memory block 16 into 8 bit using 16 into 4 bit RAM chips. Two 16 into 4 bit RAM chips may be combined to form 16 into 8 bit memory. Here, both the chips are selected simultaneously by making chip selects active. To realize a 32 into 4 bit memory block using 16 into 4 bit memory chips, the connection diagram is as shown. Here, each RAM is used to provide 16 words. Two together provide 32 words, but only one would be active at a time. Two RAMs share the 4-bit data with only one of them enabled at a time. For selection of 32 different locations, CS bar input is used as the fifth address input A4. The address lines A3, A2, A1 and A0 are connected to the address input of each chip. When A4 equals 0, RAM 0 is active, whereas when A4 equals 1, RAM 1 is active. In the example discussed, we may view each RAM as providing a page of 16 words and two together is providing 32 words. The address span of RAM 0 is from 0 to 15 and that of RAM 1 is from 16 to 31. The CS bar input provides for RAM 0 page address as 0 and RAM 1 page address as 1. Here, starting address of the memory block is 0. The starting address of a memory block is called its base address. Let us now take a more involved example which will reinforce our idea about page address decoding. If the page address of 32 into 4 bit is 7 and the width of the system address bus is 8, then the least significant 5 bits, that is A0 to A4, will be used to specify any location within 32 into 4 bit memory. And the remaining 3 bits, A5 to A7, are used to specify the page address. The page address decoding is done with a 3 to 8 decoder and output of the decoder is connected to the CS bar input of the memory block. The blocks of memory locations allocated to ROM and RAM are usually shown pictorially in a diagram known as memory map. Besides random access type of memory, there is yet another type of memory known as sequential access memory. Magnetic tape is an example of sequential access memory wherein data are to be read out in the same sequence as they are stored. That is, access time to retrieve an information would be different depending on where we are present. In microcomputer, data and programs are stored in 3 forms. Main memory or primary storage is directly addressable through the microcomputer address bus. All executable programs must reside in this memory during execution by CPU. Cache memory is a special onboard memory block used for speeding up computation. Magnetic tapes and floppy diskettes are secondary storage memories. These are used to store programs and data in the form of a file for future use. Well, friends, I have tried to provide you an overview of memory organization, its working principles, and functional classifications, and how memory chips could be cascaded to form the desired memory block. In the earlier lessons, we have talked about architectural and hardware aspects of microprocessor. In the lessons to follow, you will learn how a microprocessor can be programmed. Thank you.